So I like that quote. Try not to worry. And so thinking about the plant body, with the roots and the stems and the leaves for sure are the most diverse in morphology. If you have lived your life to date and have eyes, you've noticed that leaves can be extremely varied in their shape and design, their size. I mean, I've even seen video of, big heavy water birds walking across these giant lily pads, so to speak. And mainly because the architecture underneath, what you can't see is quite well designed to be able to hold the leaves up and flat and sturdy. I think there was even a video of a little kid sitting on one. Have you ever seen that?
I think so.
Yeah, there's a little kid just like sitting cross-legged on one. So, and then you get leaves like this. The head is separate. Yeah. That's not part of the plant, but I mean, it just for comparison, so you can see the size difference. I mean, yikes.
Barb,
Huh?
can you eat that
I
giant?
don't know. I don't know. It's a good question. Dinosaur food, they make it sound like you could, but I don't know. I've never seen one with my own eyes, but apparently people down south landscape with them. Look at that. Isn't that something? I've seen smaller ones like this. There's one house near campus actually that had a patch, but they weren't this big. Um, I don't know if they cut that down by now or not. It's been a while since I've driven by there, but anyway, so you can get some pretty impressive leaves. So when you look at leaves, there's a few things to consider for this. Now, if you buy a field guide to plants and are trying to identify plants that you go out and you're hiking around and you're like, oh, I wonder what kind of plant this is. Some of this terminology is important, but I'm not going to ask you to memorize a lot of this, but just be aware that you'll come across terminology in those field guides. By the way, do you have Google Lens on your phones? Oh, is that nice? It's usually pretty accurate. You take a picture and hit Google Lens and it'll pop up what you're looking at. So I've used that a lot lately. So that's another option too, if you don't have a field guide and you have your phone. So a couple of things. I would like you to know this idea of alternate. Where the leaves are attached, they alternate up the stem. Or if they're opposite, it's pretty self-explanatory. And then please know the world design, where they 3 or more leaves attached at one spot on the stem. Those are the 3 that I would like you to think about. And just recognize that there are other terms out there. They also look at, if you're trying to identify plants, you can look at how complicated are their leaves. You certainly can see some options here. So compound versus simple. I'll get into that a little bit more, what those mean. I'll show you some better pictures that can help with that. And then just the shape, looking at the overall shape, they often also talk about what's going on with the perimeter of the leaf. What's that going, is it smooth like that or serrated? So they do look at those ideas too. So if you're wondering if what you're looking at is a simple leaf or a compound leaf, what you have to find is the axillary bud. That will help you decide. And so if you find an axillary bud, whatever's coming off of that is a leaf. And then you might say, well, isn't that a leaf and that a leaf and that? No, these are leaflets, right? They're leaflets. The whole thing is a leaf. So here is another example over here where you see the axillary bud and that's the leaf. Okay, so trying to decide if it's a compound leaf or simple, you have to shoot for the axillary bud. That's what you have to look for, and that will tell you. Here's another image. So this one, they didn't attach the If I ever ask you to identify, I would give you the axillary bud. This doesn't give it, but they're trying to show the difference here. This picture's better because it's attached and you can see the axillary bud. And so you can examine this carefully and you're like, okay, there's no axillary bud, nothing there on these leaflets. So you know that the entire thing then would be called a compound leaf. Right, so that's the trick. Here, you can see these are each a leaf because of the axillary buds that look to be actually active right now. They're growing out more leaves or branches. All right, so that's what you're shooting for. You're looking for the axillary buds. All right, so that is one way to start thinking about what you got there in terms of leaf design. And then the other thing that I didn't really appreciate till I was in college is the idea that so many plant species, how they look when they're really young and just a seedling can vary than when they grow up and become an adult. Their leaf shape can be different. So this is just one example. So this is the same plant species. It's just that the one on the left is when it initially grows. So it's juvenile phase, essentially. It's pre-adult phase. And then the one on the right is once it's passed through its version of puberty, juvenile phase is done, you're into the adult phase. You can see the leaves have shifted their morphology. So if you're ever trying to identify a plant, it's good to know approximate age so that you can be aware that you might be fooled by the design of the leaves. If they're really young still, they can be looking differently than the mature version that maybe you're more used to. Okay, so just be careful with that. That can get really tricky too with gymnosperm seedlings. That's a pain because they all start out with just single needles. They don't group their needles right away. So it's like, I don't know what it is. So that's interesting. Margin of the leaf, like I said, they're looking at that when they try to identify. I'm not going to ask you for those words, but understand that the margin of the leaf is an important thing to zoom in on. The venation, though, I will ask you. And so parallel, that's pretty obvious. You have most of the veins are nicely laid down parallel to each other. And then you have the net venation pattern, where it looks more like a fishing net design of all the veins, both the major and minor veins. You can see have that net-like configuration. Another picture showing that a little bit better here. So these veins are running parallel to each other on the right, and then you can nicely see the netted venation. And so the reason that we, want you to think about these is this will help you to decide also if you're looking at a monocot versus a dicot. So we'll get into that. A nice venation pattern again. And here's a really nice netted. So what they've done here is actually, it was quite popular during the Victorian era, where they would take a leaf and kind of digest away all of the leaf cells except for the vascular tissue, the veins. And so I've tried this. There was a lab exercise that I've tried it a few times, but we couldn't get the tissue to fully dissolve away. And I didn't want to resort to more aggressive chemicals, so we called it quits and didn't do it. But anyways, it used to be an art form during the Victorian age. They would do this as part of their artistic endeavors. And so here, depending on what you're looking at under the microscope, sometimes you would be, like we've looked at certain leaves already. I think maybe back when we were covering the C4 cycle, we looked at a leaf in cross section where all the veins were parallel to each other. And so if you cut a leaf in cross section and then look at that, you see that all the veins look the same, you know that they're parallel veins that were part of that leaf. And then I'll show you an example of a netted venation, what you would see under the microscope as well. So you've seen this. We've looked at artistic renderings of leaves, and this is a very common representation. So if you look at the way the artist drew this, where are the stomata showing up? Top or bottom, or both? Bottom. Okay. So that's something you should clue in on when you're looking at leaf tissue under the microscope, because that's actually evidence to help you figure out what's going on with this plant. The artist, the way that she drew this, he or she drew this, I'm pretty confident they're imagining a leaf that spends most of its day in a more horizontal position to the ground rather than vertical. So the leaf blade is more horizontal. And one of the reasons I come to that conclusion is, where are the stomata? So if you're a plant and this is going now, thinking about transpiration and that precious water that plants have to really keep a close eye on. If you are a plant and you have to deal with, I have to have enough water, I gotta conserve where necessary, might have to close my stomata down, I don't want to transpire too fast and get dehydrated. So if you tuck your stomata on the underside, that will actually help you better control the loss of water from your body. And I'll try to get into that a little bit more, because I'm going to talk a little bit more about transpiration again, now that we're at the leaves. But basically, if you put your stomata on the dark side where it's shaded, you create a situation where water vapor won't be lost as quickly from your body. It's a little bit slower process because the stomata are shaded, it's cooler under there, it's a little bit more humid under there. You're not getting beat on by direct sunlight. All right, so that's something to look at when you're looking at leaves next week in the lab. The other reason I say that this was probably a leaf they're thinking is horizontal to the ground is this design of very definite palisade parenchyma cells and spongy parenchyma cells. You tend to see that design, internal design, with leaves that are more horizontal to the ground. And so what I tend to do when I look at a piece of leaf under the microscope, I kind of mentally cut the image of the interior of the leaf in half. And I say, does the upper half, is it symmetrical or look like pretty identical to the bottom? And so this is clearly not symmetrical or identical. You have, if you cut this in half, you have palisade parenchyma cells on the top, spongy on the bottom. That's another clue that the leaf probably hangs out mostly like horizontal to the ground. Okay, and I'll show you some examples that go the other way. So you've already looked at the epidermal cells in tissue in lab. And so you know that you can see a little bit of different design. Sometimes it looks like a jigsaw puzzle, sometimes it looks like a brick wall. But you definitely have those stomata to zoom in on, the guard cells that are guarding the pore. This is an electron microscope picture. These are guard cells as well. They call them dumbbell guard cells because they look like dumbbells that you lift weights with. And much more elongated pore, but it still does the same thing. They still move by this idea of water rushing into the guard cells, and it causes the guard cells to move away from each other. So it's the same mechanism, they just have a slightly different design. So there is some morphological differences too. You tend to see this kind of dumbbell design in monocots. It's not 100%, but you often do see that. So when you look at the guard cells, I wanted to talk to you a little bit more about this process of how are they moving. And this slide does a pretty good job of explaining. So you see all of these black lines, right? These are what we call radial. It's a radial design, like steel belt radial tires. And because of that design, that creates a world of difference on how these cells behave when they get full of water. And so when you have water rushing in to the guard cells, because of those, the fancy word is radial myceliation. I don't even know if I can write that word out, so long. Radial myceliation. That's supposed to be a C. Radial myceliation. All right, so that's in the cell wall. So these are microfibrils that are laid down at these angles like that, the radial angles. And that makes all the difference when you have the water rushing in. If my hands are the guard cell, when the water rushes in and presses the turgor pressure, you know, water pressure pressing against the cell wall, and those radial microfibrils causes them to kind of bend away from each other. And that makes all the difference. The physics of it makes it so that when water presses against those radial microfibrils, it causes that kind of bending away from each other. And that's what reveals the pore. So it's totally different than when I was first learning. When I thought, well, water must leave the guard cells for them to open, but it's the exact opposite. And it wasn't until someone explained to me these radial myceliations that it finally, it's like, oh, okay, that does make sense. So water rushes into the guard cells, that opens the pore. Water rushes out, you'll get the turgor pressure is lost. And so they go and close over the pore, right? Does that make sense? Okay. So the plants have to devise a way to do that without expending a ton of energy and causing, you know, issues with their reserves in their body. So a pretty easy way to do that, and they're trying to show this in figure C, is to play with osmosis, the idea of osmosis. And so osmosis is the movement of water across a membrane, right? And so here, if you pack all these red balls that you see in the top picture, that's potassium. If you pack those guard cells full of potassium, you're creating a concentration gradient where you have a lot of solutes, potassium, building up in the guard cells compared to the neighboring cells around them. And so that will cause water to want to rush in to dilute out all those concentrated ions. And that's what you see happening. So when the plant's like, I want to open my stomata, and now granted, please understand, I'm simplifying this. It's when you look at what's going on in the cell molecular biology of it, it's a lot, but actually it's quite elegant. Because you have this very stepwise process where ultimately you end up getting potassium flowing in to these cells, and then water will follow. And that's what's creating the water pressure. And then if they want to close their stomata, they just do the opposite. They get those solutes to leave the guard cells. Water will follow that through the laws of osmosis, and they'll relax and cover over the pore. So that's what they're trying to show in figure C, with, you know, the inrushing of water when you have lots of potassium in there, and then water leaving when you have the reverse happening, where you have more potassium in the nearby cells compared to the guard cells. Okay. So hopefully a plant living its life wherever it's found, when, especially, you know, if you think about temperate, you know, summers here, when the sun comes up in the summer, they're going to want to open up their stomata because they want to do photosynthesis. But remember, as soon as they do that, they start to lose water out of their body through the process of transpiration. So let's revisit that idea. So this is often how they talk about this, these two concepts. Yeah, they want to do photosynthesis, but as soon as they do open their stomata, they're losing water. And so they call it a compromise. It's a transpiration photosynthesis compromise. And it's not something, it's not like the plant can say, water, stay in. You know, you just can't do that. It's like secondhand smoke. You can't tell the smoke to stay over in that part of the restaurant. I used to laugh. We go into restaurants and there's a non-smoking area and a smoking area. I'm like, what, did they train the smoke just to stay over there? You know, it doesn't work. But anyways, so you have this lots of water. So what they're trying to show here is that you have water evaporating from inside the leaf. And then once it becomes vapor inside the leaf, it'll exit out as water vapor. And so what's happening is, let me show a vein. If you can imagine the veins of the leaf where water is coming up through the xylem. And what happens is water kind of oozes out of the vein and the liquid water kind of clings to the surface of these cells inside the leaf. And then the liquid water starts to evaporate and becomes water vapor and then goes out as water vapor. So as long as all those liquid water molecules are all connected through cohesion, they all like to hang out with each other and touch each other and be with each other. So that's a cohesive force. As long as all that liquid is like a solid, not really solid, but a steady column where they're all connected, you can have water literally being sucked up the plant, because as soon as you open the stomata, you get a tension force. Remember, we talked about that last week or so. So as soon as that happens, as soon as the stomata open, you will have a tension force on the liquid water molecule, and it keeps sucking the liquid out of the vein, so to speak, onto the surface of these cells, and the water evaporates, and you just keep this constant tension gradient where you have nice tension, really nice tension developing here inside the leaf. And as long as all those liquid water molecules are connected with each other, all the way through the vein, all the way down to the roots, you'll have a steady pulling up of the water through the plant body all day long. Then at night, they can't do photosynthesis, no light. They can't even do the Calvin cycle, by the way. You can't do the Calvin cycle at night because some of the enzymes needed for the Calvin cycle need light to be activated. So they take a nap when it comes to photosynthesis at night, close their stomata because now they don't need them open. And that releases the tension, right? So now the tension force is gone through the night. And so there's still liquid, you know, in the xylem, it's just not getting sucked up, right? So let's revisit the idea, okay? And so I'm mentioning this again because now we're at the leaf, and this is ultimately where the force is generated for transpiration. You gotta have the stomata open, otherwise this is not gonna work. And so the water is being brought in to the roots from the soil along with dissolved minerals, and it's unidirectional. There's only one way for it to go. Once it gets into the xylem, it's a one-way movement up the stem, the branches, the veins of the leaf, and then out as water vapor outside of the leaf. And so it's a pretty elegant design. It doesn't require, you know, it doesn't require ATP or anything like that. It's just this idea of, you know, it's a compromise. It's a compromise. Once they open the stomata, it's not like they can tell the water to stay. It's just automatically going from the laws of physics, okay? Questions on transpiration? Okay, so here they're at least showing the vein in this drawing. So you can imagine that you have the larger cells or the xylem. So you can imagine that there's liquid water coming out of there, and then they start to coat the surface of these cells, and they're all connected. All the liquid water molecules are connected. And then you have water evaporating. That's one reason why leaf tissue is designed to have good air spaces. It's for transpiration so that they can get liquid water clinging to the surface here and allow for that evaporation into the space. Another reason why they have space, air spaces like this is wind. So if you've ever looked at, you know, if this was solid, like if it was all really tight palisade parenchyma, and then you put a big shear wind force on that, it would probably cause the leaves not to. I don't know if you've ever seen leaves in like a wind tunnel where they show how the leaves can curl as the wind, you know, the what's that called when you have a, not a tornado, but a, no, it's like wind that's all in the same direction. Straight line winds, that's, yeah, that's the non-scientific term. There's another term, but straight line winds, let's go with that. So in a wind tunnel, you have straight line winds. And if you have things that are really solidly packed, they don't want to curl and bend and spill the wind off them. And so if they're too solidly built, so to speak, where there's not enough flexibility to the leaf, then the leaf just gets ripped off the branch. And so they've actually done those kinds of studies where they put trees into a wind tunnel and blast them with the wind and see what happens. But anyway, so you need those air spaces, especially for transpiration processes. And the opening of the stomata kicks it all into here. Whenever you see a leaf like this, and you see these squiggly lines right by the stomata, they're trying to show that you have frictional forces there. Just, you know, you have the guard cell opening. So if it's a really narrow opening, there's more frictional force as the water vapor molecules exit. So it'll be a little slower due to friction. The wider the pore, less friction, you know, so again, just thinking about the laws of physics here. And so you can have a plant slow down transpiration just by, you know, how wide are those, is the pore? And if you have it narrow enough, you do dramatically slow down the transpiration rate. Here, they're also showing, of course, if you do that, then you have a slower CO2 uptake into the leaf for photosynthesis. So it's a compromise. It's always a compromise. The other idea I wanted you to see here is this idea. They're saying there's a boundary layer of resistance. So this is another frictional force. Not just the sides of the guard cells right at the opening, but every solid substance has a boundary layer. Your body has a boundary layer to the atmosphere. And so you have, just like leaves do, a relatively still layer of air molecules right on your body surface. Okay, really close to your body. And the boundary layer can be thick or thin, depending on often wind. So if you can imagine now wind blowing across this leaf, what's going to happen to the boundary layer of still air? It'll be thinner, right? You're causing that still air now with that wind to not be so still anymore. And so your boundary layer gets thinner. That actually speeds up transpiration because you've caused a thinning of this resistance. These still air molecules are frictional forces of the water vapor trying to exit. So if you have a really thin boundary layer, you're going to have a faster transpiration rate. If you have a non-windy day and a really thick boundary layer, your transpiration rates will be relatively slower than if it was a windy day. If you have a really humid day, let's say it's 98% humidity and it's, 80 degrees. And then you have another plant experiencing, instead of 90%, 40% humidity. Under which condition do you think the plant would have a slower transpiration rate? Think about you sweating and you're either in 90% humidity or 40%. Where do you sweat at a slower rate, or the sweat evaporates off you at a slower rate? Yeah, 90%. So using the analogy of you sweating, like if I made you run a 5-mile run and then stuck you into a growth chamber with 90% humidity, the sweat would just cling to you. You'd just be like, oh, especially if there's no wind in there. And that's kind of analogous. Use that analogy. If you have a really humid day, you're going to have, and no wind especially, it's going to be harder because there's so much water if it's 90% humidity in the atmosphere, you have a lot of water vapor in the atmosphere around the plant. And so it's harder for the water vapor to come out into that really high humidity. It's gonna slow your transpiration down. Compared to if you put that plant in 40% relative humidity, going to be easier for those water vapor molecules to exit out. So often, if you're trying to figure that out, just think about you sweating under these different conditions.
That's like. Or is it like harder for them to pick up CO2?
Exactly. It's a compromise, right? So if they're like, I'm feeling drought down there in my roots area, they might prefer a non-windy humid day just so that they can deal with, I'm sensing drought. But then they sacrifice CO2 uptake. Yeah. So hopefully they built up enough reserves for that time stretch before they get into trouble. The other thing that I alluded to, why does it do that? It won't let me erase. I have no idea. All right, so here is the whole system, unidirectional flow. Are they showing it here? No. All right, let's finish this thought. Okay, so you have water coming in with the dissolved minerals, getting to the vascular tissue of the root, to the xylem. And then it courses up through the branch and stems, well, stems and branches, and then the leaf veins. And they're trying to show that you have, as long as all those water molecules are cohering with each other, then you're good. And so it has to be this unbroken column of water, so to speak, liquid water, all the way from the roots to the leaf in order for that tension force to be felt and draw the water up. If there's an embolism, remember we talked about embolisms? The fancy word for that in botany, and I'd like you to know it, is cavitation. Okay, so cavitation is essentially an embolism in a way for the plant. So here what they're showing is the water got taken up into the xylem, but one of the xylem structures had a big air bubble in it. So if you can imagine water coming to that point and bumping into this air gap, it's not going to be able to continue through that. It can't. And so thank goodness vascular tissue, when you look at it and you have under the microscope, you have lots of xylem all clustered together. You don't just have one xylem going from the roots to the leaf. You have a cluster. And this is why it helps them reroute. Remember, there's pores on the side of the tracheas and vessels so that water can reroute and go around any of the cavitated xylem. So that air bubble occurred probably because if you've ever done any experiments in physics where you have dissolved gases in liquid and then you start to put a tension force on that water, like if you put water into a syringe, into the plunger, you know what I mean? Like put it into the syringe and then you suck back on the plunger. And if you have dissolved gases in that column of water, they pop out of solution. So this is what happened. Remember, this is all under a tension force. If the stomata are open, the movement is caused by a tension force. So if you apply tension to dissolved gases, they're with a tipping point, you're going to reach the gases come out of solution, they pop. And that's what's happened here. So their transpiration rate actually caused this to happen. Not on purpose, but it happened. Because when plants take up water, it's not pure water. It's water with dissolved gases and minerals, all right? So if it was pure water, no problem, but it's not pure water. And so you can get cavitation to occur, especially with vessels. Okay, so vessels are more at risk because of their larger diameter. We talked about that idea. So if you have a larger diameter, it's going to be easier to get a bigger air bubble and they pop out of solution better, easier, I should say, easier. And so vessels, you have more of a risk with this. So cavitation tends to be, when do you think cavitation would be more of a risk, spring or summer? Yeah, summer? Yes, summer. Drought. Exactly. So if they do a little whoops, like, oh, we are under a drought condition and they didn't quite regulate that well enough, it can occur, especially in the vessels, that you'll get these air bubbles, these cavitation events. And it could mean that that particular vessel is useless now for the plant for the rest of the summer. There could be a way, maybe, to get that air bubble back into solution of the xylem water. Can you think of what might allow for that? What happens at night to the plant? Okay, that's the first step, the stomata close. So if they close their stomata, what happens to the force? It's like if you take a rubber band and you pull, that tension force, and then all of a sudden you release it, the rubber band goes back to its normal size. That's kind of what I imagine, where the water column is under this tension, and then you close the stomata and woof, all the tension is released, the water can kind of gather together, so to speak. And that can allow sometimes for the air bubble to go back into solution if you release that tension force. So it's not necessarily permanent, but often it's too big of an air bubble and they just can't recover from it. But sometimes they can. So cavitation, not a good idea. It's not the same thing as an embolism in a human, which typically kills the human, but it does often kill the movement of water in that particular xylem. Okay. So really, really important that water, we often refer to it as a water column through the whole xylem. It's all liquid water cohering to each other and forming like this solid column of water. Here's another idea here where they're trying to show you have unidirectional movement of water up through the plant and out as water vapor. And then they're also showing photosynthesis where they're taking in CO2 and the sugar. Now, interesting. Not really showing that. One thing I would like you to know about the sugar transport there, I thought they had it on here, but they don't. So can you tell which color is the sugar transport? The green, right? So I wish the artist would have drawn some green lines swooping like around into, from one half of the tree to the other. Because even though we know that water movement is unidirectional, phloem, the movement of sugar can be in any direction, not in the exact same phloem tissue, but remember, phloem tissue is clustered. And so if this side of the plant, the left side of the plant, maybe there's a lot of baby leaves over there that are like, I can't do enough photosynthesis on my own, I need help. And maybe the mature leaves over here are like, well, I can give you some. And so they can reroute the sugar into that direction. So it's a lateral movement. They can route the sugar, of course, from the leaves where everything's, making the sugar. And of course, they can get it to the roots, like what's being shown here. But you can have sugar movement in any direction. Okay. So it's very different in that regard compared to water movement. Sugar movement's much more flexible, and it really just depends. The plant is paying attention to which part of its body needs sugar, which is topped off and it's good. And it senses those signals and is able to deliver sugar where it's needed, no matter where. And so it's a lot more flexible in that regard. Okay. Questions on that idea? Here's a leaf in cross section.
Probably if you look, you can see this is a major vein. The other veins are much more scarce. Really hard to see. I wouldn't expect you to pick those out. Those are hard. Okay, so these veins are all looking the same in this image, right? So when they took the cross section, all the veins are in cross section. They're all coming out at you. You have to imagine, the leaf extending out at you. Leaves are coming straight out at you. So is that netted or parallel venation? Parallel. It's parallel venation. Now, the other trick is to cut the leaf in half. Is the top half of the image the same as what you see below? No. So that means this leaf is spending most of its time horizontal to the ground. The other thing to look for are the stomata. That's tricky on this image. It looks like there's one kind of smushed one here. Maybe one here somewhere. Whoops. But up here, you don't see, there's no stomata up here. So that's another giveaway that they're tucking the stomata in the cool, humid section of their tissue, their leaf tissue, away from direct sunlight. So you can actually get a fair bit of information from a leaf under the microscope. You can get a little bit of a feel for this plant's lifestyle in terms of the venation pattern, how they are putting their leaves through the day. This is another example of leaf morphology can change, and this is off of one plant. All right, so this is maple. This is a maple tree with leaves that were taken from parts of the canopy that were in direct sun and parts that were in a shade leaf. So sun leaf, shade leaf from the same tree. And you can definitely see the morphology is different. And so they can do that. They can adapt their leaf design in their own lifetime, depending on if they're sensing they're in direct sun or if they're in shade. And so typically, if you see a comparison like this, it's typically the sun leaf that is thicker in cross section. You'll see it's kind of beefed up because it's like, oh man, I'm in direct sun. I'm going to take so much advantage of this. I'm going to pack my tissues full of all these cells that can do photosynthesis. So you really get a thicker leaf, but not really bigger in surface area. Okay, thicker. If you're a shade leaf, you're like, I'm getting shaded. I want to try to see if I can get some sun. And so you'll spread out your tissue. You'll have a bigger surface area and be thinner and compromised to that. Okay, and so you can see that if you ever really look carefully at an older tree and look at the lower leaves that are more shaded compared to upper leaves. So it's really nice that they have this flexibility in their overall design when you look at these bigger plants that have, parts of their body that are more consistently shaded than other parts. So maple leaves. So again, if you look at this, cut it in half. Again, you can say, well, maple leaves, they are pretty much horizontal to the ground, and this asymmetrical, they look different on either side of that halfway point is telling. Also the stomata, you can see stomata on the bottom and not on the top. This is kind of hard to tell, but this is a plant that has its leaves more vertical to the ground. And so that's what I'm trying to get across there. Oh, okay. So this is a vertical leaf with a few things going on here. Okay. So first, let's cut it in half and look at the parenchyma cells in there. So do you see pretty symmetrical views here? Yep. So you have pretty similar tissue design above the red line compared to here. So that is pretty much a dead giveaway that this leaf is more vertical to the ground. Then you look for stomata, or maybe you look for stomata first, it doesn't matter. And you can see, oh, here's some stomata up here. Oh, look at that. There's some stomata down there too. So if you are a plant who has its leaves vertical and you live your life out in the great, wonderful nature, and then sunrise, so east would be this direction, sunrise comes up and hits this side of your leaf half the day, and you have high noon, and then as the sun is falling, it's hitting this half of the leaf half the day. It doesn't matter where you put your stomata. Doesn't matter. You're going to get sun on both sides of the leaf, pretty even Steven. And so that's what they do. They just leave stomata kind of evenly scattered on both sides of that vertical. There's something else going on here. What did I circle, do you think? Well, look at this one anyways. What's this? Vein, vascular tissue. So is that. Okay, so when the technician took this leaf and made a slice, he managed to cut this vein in half. But this vein must have been going this way, and he sliced along the length of it. Does that make sense? So is this parallel or netted? Netted, very good. So you can get a lot just from looking at this. Once you train your eye and learn a few basics of the rules, you can tell a lot about some of the leaves and plants that you're looking at. Okay, we'll stop there. Have a good weekend and stay safe, everybody. And we'll see you on Monday. Remember to do that lab quiz.